Okay, so yesterday we looked at density curves. What is the area under any density curve? It's always one. Okay, and that corresponds to the proportion of data that is under the curve. Okay, and we also looked at normal distributions. Okay, and so a normal distribution is symmetric, it's bell-shaped. All right, lots of things in life are normally or approximately normally distributed. And so we can standardize. The standard normal distribution has a mean of 0, right? Let's get a go in this morning. And it has standard deviation of 1. That's the standard normal distribution, okay, which we use to find the proportion of data under the curve using normal CDF, okay? So that's a quick summary of what we did yesterday. I'm going to continue here in part C. It says, what percent of Rafael Nadal's first serves are between 100 and 110 miles per hour? And remember, we have a normal distribution here with a mean of 115 miles per hour and a standard deviation of 6. So if I want to find the percent that's between 100 and 110, I need to standardize both of these. So I need to find a z-score for both of these. So let's write it like this. I want the probability that X is between 100 and 110. So I'm going to find z-scores for both of those. So we've got 100, and it's always the observation minus mu, which in this case is 115. And then we divide that by sigma. All right, so that's going to be -15 divided by 6, which is -2.5. So that's my z-score with 100. And now I'm going to find the z-score for 110. So we've got 110 minus 115 divided by 6. And that's -5.6. So that will be -0.833. So after I have my two z-scores, I'm going to put those z-scores into normal CDF. So normal CDF, and the lower bound would be -2.5. Upper bound would be -0.833. And then mu and sigma are 0 and 1. And label them. Okay. So lower bound, upper bound, mu, sigma. And so now take your calculator. And let's go to normal CDF. Okay, so go to the scratch pad. And then we go to menu, statistics, distributions, and normal CDF. And it's going to prompt me for the lower and upper bounds, and then mu and sigma. So make sure you get the negatives, right? It's -2.5 for the lower bound. The upper bound was -0.833, I believe. And then mu and sigma are 0 and 1. And I'm going to hit OK. And so I get 0.196 for that proportion. And so let me go back to the notes here. And so this is 0.196. So I'm going to say about, okay, when you write a conclusion here, you need to put it in context. So I'm gonna say about 20% of the serves are between 100 and 110 miles per hour. Okay, well, here we're going to work backwards a little bit. It says the fastest 30% of Nadal's first serves go at least what speed? So let me draw a little normal distribution. The mean is at 1/15. And so this time we are looking for a speed. So I'm going to call that X. And what information do they give us? It's the fastest 30%. So that means if I were to shade in this right here, then this has to be 30%. And so the way that we work this problem, we're working backwards from normal CDF. If we have normal CDF, we do lower bound z-score to upper bound z-score, mu and sigma, 0 and 1. Okay, but if we need to find a z-score, then this is your, I said you had new stats friends yesterday, normal CDF. Well, this is inverse norm. Inverse norm. Okay, and so we use inverse norm to get a z-score when they give us a percentage or an area under the density curve. And here's the key to inverse norm, okay? It's always the percentage to the left. Okay, so from X right here, what percentage of the data is to the left? Well, that would be 70. So I need to put in 0.7 right here. And then mu and sigma are standardized also. So 0 and 1. So I'm gonna make myself a little note here. This is area to the left. So let's take our calculators. And you're going to go to menu, statistics, distributions again. But instead of normal CDF, the one under it is inverse normal. So I'm going to choose that one. And then it's going to ask for the area. So I'm going to put in 0.7. And make sure that the area there is a decimal, right? It has to be. It has to be less than 1. Okay, otherwise you will get an error. So I'm going to put in 0.7, 0 and 1 are there and hit OK. And it gives me 0.524. Okay, so let's go back to the notes here. And I have this is 0.524. However, I haven't answered the question yet. What did they ask? What was the speed? And so if you do inverse norm, that will give you the z-score. So let me set up the equation there. 0.524 is my z-score. So I'm going to set that equal to my z-score equation, which is some speed minus the mean, 115, divided by the standard deviation. And then I'm going to algebraically solve for X. Okay, so take your calculators and we would multiply 0.524 times 6. And then I add 115 to that to solve for x. And so I get x equals. So do the math there. And I got 118.146 miles per hour. Yes.
It's supposed to use the exact value, or is it fine if we use the round?
It's fine if you round in this case. That's no problem. There, okay, but just show your work, okay? I think rounding matters only if we're talking about something like human beings or something like that, okay? Or there's another situation later on where rounding might matter, but here it doesn't so much. Just show your work, okay? Write down inverse norm, write down the z-score, set up the equation. Okay, show your work. Okay, so let's do one more here. It says a different player has a standard deviation of 8 miles per hour on his first serves, and 20% of his serves go less than 100 miles per hour. If the distribution of his serve speeds is approximately normal, what is his average first serve speed? Okay, so let me make a little sketch here. And the mean, they do not tell me. In fact, that is what I am looking for because it asks what is his average first serve speed. They do tell me the information that they give me. The standard deviation here is going to be 8. And then they also tell me that 20% are less than 100. So I'm going to set this up with inverse norm. What is my area? The area 0.2. Okay. It's always the area to the left of the value. And then mu and sigma are 0 and 1. Okay, so take your calculators and do inverse norm of 0.2, 0 and 1. And my z-score here is going to be negative. Why is my z-score negative? It's less than the mean. And just like in this one, I probably should have asked you this question. Is 118 miles per hour a reasonable answer in the context of the problem? Considering that it's the fastest 30%. Yes. Okay, so we just always want to self-check our answers there. Okay, what is this z-score here? Should be negative 0.842. Okay, so now I can set up an equation. So I've got negative 0.842 equals x, and x in this case is going to be 100. That's the information that they gave me. Minus the mean, which is what I'm looking for. So minus mu divided by the standard deviation, which is 8. And so now I'm going to algebraically solve for mu. So multiply negative 0.842 times 8. and then subtract 100, and then divide by -1. And again, mu should be a positive value in the context of the problem. It has to be positive, right? Because we're dealing with speed, miles per hour. And so check your answer with your neighbor there. Let's make sure we did the algebra right. And if your neighbor needs help, help them out. And then check with mine. I got 106.733 miles per hour. Okay, so there are two main things that we are looking at today to finish up this lesson, okay? Yesterday we did normal CDF, which goes from z-score to, excuse me, it goes from lower bound to upper bound, which are z-scores there, unless it's infinity. Today we look at inverse norm, which is what we do when we have an area and we want to find a z-score. And then the last thing that we are going to do is this, okay? Just because a plot of the data looks normal, we can't say that the distribution is normal. And so there's a normal probability plot to check for normality. A normal probability plot provides a good assessment of whether a data set follows a normal distribution. Okay, and so we are going to look at this, but first, I think I want to go ahead and write this down. How do we check for normality? Okay. We're going to put in the data, and then we're going to take that data and put it into what's called a normal probability plot. And we check to see how linear that plot is. So I'm going to write myself a little note here. Check to see how linear the plot is. Linearity implies normality in a normal probability plot. And so this might be a multiple choice question, for example, on the AP exam, and they give you a normal probability plot and they ask you, does the plot justify normality or not? And you're checking to see how linear the plot is. So here's what I want you to do. We are looking at capacity of refrigerators. And so I need you to get this data into the spreadsheet. So do that for me, please. So to do a normal probability plot, we put the data into the calculators. So now I want to add a page. So Control Doc, and then I want to do add data and statistics, which is option number 5. And then we do click to add variable, and I want to choose the name of the variable, which in this case is capacity, and it should give you a standard dot plot, which is kind of the default plot. So now I'm going to put my cursor up above the dots there, and I want to go to menu, plot type, and then I'm going to choose option number 4, which is a normal probability plot. And what am I looking for in the normal probability plot? I'm looking for linearity. Okay, does it look linear? It does. Okay, And so again, what does the normal probability plot show? It shows is the data that we have an approximately normal distribution. And in this case, I would say yes, because how linear is the normal probability plot? Pretty linear, okay? And so I'm guessing, right? It's possible you might have this on a free response question on the AP exam. More than likely, it would probably be a multiple choice where they would give you this and ask, is the data approximately normal or not? And you're checking for linearity, something like that. Okay, so again, two things today. Inverse norm, which is where we take the area and go back to a z-score. And normal probability plot, which is where we're checking to see if a distribution is normal. And we do that by graphing the data points and running a normal probability plot and checking to see how linear that plot is. Questions for me?